Okay, happy, lovely spring Monday morning, everybody. So last time we ended class talking about percent composition, and I gave you a kind of challenge to try to determine what the percent composition of each element was in N2O5. Okay, so we're starting today just breezing through the answer to this, okay? All right, so if you are given a formula and you're asked what's the percent composition of this element, right? The first thing you need to know is the mass of the compound, okay? So you would have to figure out the molar mass of N2O5. So that's adding up all of the masses of the individual atoms that make up one molecule of this compound. Okay, so in this compound, we have 2 nitrogen atoms at 14.007 grams per mole apiece. Okay, and so the mass due to the nitrogen is 28.014 grams per mole. And then we have 5 oxygen atoms, okay, at around 16 grams per mole apiece. So 5 times 16 is 79.995 grams per mole. So that's the mass due to the oxygen. Okay. So in this example, okay, the mass of the compound, the molar mass of the compound, is 108.009 grams per mole. So to figure out what percent is due to the nitrogen, what percent is due to the oxygen, right? We just take the mass due to the nitrogen, okay, which is our 28.014, and divide it by the total mass of the compound and multiply by 100%. And if you're wondering why I didn't write the grams per mole, it's just because they cancel, and I was being lazy this morning when I wrote this out. So. All right, so 25.94% is due to the nitrogen, and 74.06% is due to the oxygen, okay? And so just to double check, these should add up to 100%, right? When you add up the individual percentages for each of the elements that make up the compound, they should all add up to 100%, and in fact, they do. Okay. All right, so now what we're going to do is we're going to do calculations that are a little more reflective of how folks use percent composition. And that, excuse me, that is to figure out a formula, okay, from experimental measurements where you determine the percent composition of each element, okay? So the whole point is figuring out formulas from experimental data, okay? From experimental data. Okay. All right. So whenever we do these, we're always if we're given percent composition, we always kind of assume that we have 100 grams of the compound. Okay, so percent means parts out of 100. So if we have 74% of oxygen in our compound, we can say that if we had 100 grams of that compound, 74 grams would be due to the oxygen. Okay, so I'm just going to, whoops, that is not what I wanted to do. I wanted to change the pen. So, in 100 grams of N2O5, 74.06 grams are due to oxygen. That's how you should interpret that percentage, okay? Okay, so when we're dealing with, percent compositions and we're trying to figure out a molecular formula, okay, just take those percentages and the parts out of 100, and we're going to say grams out of 100 grams, okay? All right, so what we're going to do is for each element, okay, if we're given percent composition, okay, the percent composition in grams is going to be equal to how much of, that element's mass is there, okay? Then, because we need to, if we're figuring out a formula, right, a formula tells us number of atoms of each element that are in the compound. Okay, so that is number of objects of a certain type. When we're talking about number of objects, we have to go through the unit of the mole, okay? So we're going to go from percent composition, okay, to grams, and that's not going to involve any mathematics. It's going to just involve changing the percent symbol to a G, okay? And then we're going to go from grams to mole, and this is the molar mass of the element is what we're going to use. Okay. And then what we're going to do is we are going to compare the relative amounts, okay, of each element, okay, by dividing by the number of moles of the element with the lowest number of moles. And that's going to get us to our formula, okay? So these are our 3 steps. 1, 2, and 3. 1, 2, and 3. Okay. Okay, so we're gonna run through an example of this. All right. So in this example, okay, we're given percent composition. Okay, so this is what we're starting with. So we've done an experiment in the lab, and we figure out that this compound is 41% potassium, 33% sulfur, 25% oxygen. Okay. All right. So on this slide, we're doing what I called step 1 on the, or step 1 and 2 on the previous slide. Okay. So step 1 is assume you have 100 grams of the compound. And so what that means is that we have 41.09 grams of potassium, 33.70 grams of sulfur, and 25.22 grams of oxygen. Okay. All right. So then, step 2 is, again, to figure out how many moles, okay, of each of those elements is there. How many moles of each element? And again, in this case, we're going to use the molar masses from the periodic table. So, the 2 things you should always have by your side for this in the next chapter are your periodic table and a calculator, right? Because we're talking about reactions, we're figuring things out. So, and I always have a bunch of periodic tables over on the lectern here. All right, so this is the molar mass from the periodic table of potassium. Okay, and so we are doing unit conversions from grams to moles, right? All right, so I figured out that I have 1.05 moles of potassium, 1.05 moles of sulfur, and 1.576 moles of oxygen. Okay. Well, that doesn't necessarily help me get to the final formula. There's something else we need to do, because those are not integers, right? you can't have 1.5 oxygen atoms. It's just not a possibility. Okay, so what we then do, okay, is our step 3, okay? And step 3, okay, so we figured out number of moles. And step 3, okay, is to divide by the lowest number of moles. And the reason we do that, right, is what we want to do is we want to get to integers. What's the simplest integer we can get to? The number 1, right? And how do we get to the number 1? Well, we take the smallest number. Now, in this case, okay, we have 2 elements that have the same amount of moles, okay? So we can immediately know that there's going to be a 1-to-1 ratio of those elements in our compound, okay? But if we want to figure out the overall, what we call compound stoichiometry, which is what we're doing right now, okay, so what we're doing is called compound stoichiometry. When we talk about chemical reactions, we will talk about reaction stoichiometry. So compound stoichiometry is the molar ratio of elements in a compound. All right, so when we divide by that smallest number, we're going to divide everything by 1.051. What we get is we get 1 mole potassium, 1 mole sulfur, and 1.5 moles of oxygen. Do we have 3 integers yet? No, we have 2 integers and 1 non-integer, right? So right now, okay, as of this point, our formula we could write as KSO 1.5, okay? But we cannot have, half an atom, okay? So the easiest way to get everybody to a integer, okay, is to multiply, okay, by a number that will give you an integer. What can we multiply 1.5 by to get to an integer? 2, right? So if we multiply everything by 2, what we get is K2S2O3, okay? So this is the actual formula for our compound. Okay, so this is what we call the empirical formula for the compound. Now, it might not be the molecular formula for the compound. We're going to talk about that in a minute, okay? So, again, when you do this process, you are not always going to come out with every number being an integer, and in that case, then you need to multiply everything by some number that's going to get you to that integer, right? And so there's a little helpful table here, okay, so if, for example, okay, you wind up having, one of your numbers is 1.2, okay, then your formula will wind up being A5B6, right, and so on and so forth. So if you look, we had 1.5. This was the previous example, right? Oops. Where one of our things wound up being 1.5. And so our formula wound up being, right, where we had 3 of the oxygens, and then the other 2 elements we had 2 of, okay? All right. So, all right. So the next thing what we're going to do is we're going to talk about empirical formula versus molecular formula. Okay, so, in this case, okay, we have three elements, or two elements, sorry. We've got carbon and hydrogen. Right? So our goal is to figure out what X and Y are. What are the subscripts for the carbon and the hydrogen? Okay? And so if we have our empirical formula, okay, in both of these cases, okay, we have 2 hydrogens for every carbon, right? So cyclopropane, okay, has its empirical formula, okay, is CH2. That's how many hydrogens per each carbon, right? So this is empirical formula for both is CH2. If you count up all the carbons in cyclobutane, you also have CH2 as the empirical formula. Okay, so, oops, I'm going to erase that because I put it up here. All right, so now the molecular formula for each is different, right? So the molecular formula for cyclopropane is C3, okay, and then H6, right, for that. And then for cyclobutane, we've got 4 carbons, and we've got 8 hydrogens, okay? So if we did an experiment, okay, where we just determined percent composition, okay, we would wind up getting the same empirical formula for both of these compounds, but they are not the same chemical. Do we all agree they're not the same chemical? Okay. They certainly don't behave the same way, okay? All right, so we need another piece of information to distinguish what is the chemical we have, okay? So we've got the same empirical formula. And we need another piece of data. To determine the molecular formula. Okay, and that other piece of information, okay, is the molar mass of the compound, okay? So, for example, okay, just to give you an idea of how one could figure out molar mass of the compound. These molecules, excuse me, these molecules are not acids, but in lab last week, you did an experiment, a titration, that enabled you to figure out what the molar mass of the compound that was in the unknown was, okay? So you could do that type of experiment if your unknown chemical is an acid. You can do that to figure out what the molar mass is, and then you could combine that with percent composition to figure out what we have in terms of a molecular formula and an empirical formula. All right, so in this case, okay, if we take the empirical formula, okay, we could figure out its molar mass, right? We've got 1 carbon, 2 hydrogens. Carbon's molar mass is 12, hydrogen's 1. So when we've got 2 hydrogen atoms and 1 carbon, we got a molar mass of 14.03. All right. And when we determine the molar mass of the compound in question, okay, we find out that its molar mass is 56.11 grams. Okay, and so we have one chemical, okay, where the molar mass is going to be the sum of 6 hydrogens plus 3 carbons, and one where it's 4 carbons, and 8 hydrogens, okay? So if we want to talk about these two compounds, in terms of how many multiples they are of this basic formula, okay? So C3H6 is a multiple of what? Of CH2. It's 3, right? We take CH2, multiply it by 3, and you get C3H6, right? And then C4H8 is a multiple of 4 of the empirical formula. So the molar masses of these compounds, okay, will be either a multiple of 3 or a multiple of 4 of the molar mass of the empirical formula. So to figure out which one we have, okay, we're going to take the molar mass of the compound, okay, 56.11, and figure out what multiple it is of 14.03. So we're just going to divide by 14.03 grams. And survey says 56.11 divided by 56.11 divided by 14.03. If I can type it into my calculator right, it comes out to be 4. So which of these two compounds did I actually have in my experiment? Did I have cyclopropane or cyclobutane? I have cyclobutane, yes. That's the one we got. All right. So the basic procedure, for doing this is for each element, right? We're going to figure out the mass in grams from percent composition. We're going to convert grams to mole for each element, and we're going to get our empirical formula, okay? And then if we have a molar mass for the compound from experiment, we're going to compare the empirical formula molar mass to the compound molar mass, right? So we're going to take the empirical formula, and we're going to divide it by the compound mass. And that's going to give us a number, and that number is what we're going to multiply the subscripts in our empirical formula by to get our compound formula, okay? So the last thing we're going to do is we're going to multiply subscripts in empirical formula by the number, and this is going to be rounded to an integer. And in real data, theoretical data, it's going to round very nicely to an integer. When you have real data, you have experimental error, so you might get something like 3.97 or something like that. But you're going to round to the nearest integer, and you're going to multiply those to get the molecular formula. Okay, so empirical formula is just the relative proportion of elements to one another in the compound. The molecular formula is actually, how many moles of each, or how many atoms of each element there are. Okay. All right, so we're going to do an example of this. We're going to determine a a molecular formula and an empirical formula, okay, for a compound where we have a molar mass of 110.11 grams per mole. So that's the piece of information we're going to use last, okay? What we're going to use before that are our percent compositions. So we've got oxygen, hydrogen, and carbon, okay? So for each of these, okay, we are going to first start by figuring out the mass ratio, okay, or the molar ratio. So what I'm going to do is just divide the screen up a little bit. All right, so we've got 65.45% carbon. So how many grams of carbon am I going to say that I have if I have 100 grams in my sample? Yeah. Yep. So I have 65.45 grams of carbon. And I want to know how many moles that is, right? So step one is going from percent composition to moles of each element. Okay, so we're going to have the molar mass, right? And we're going to put the grams on the bottom. We get the molar mass of carbon from the periodic table, right? 12.011 grams per 1 mole. All right, so that comes out to be 5.449 moles of carbon, okay? All right, so next up is hydrogen, 5.493 grams of hydrogen. And in 1 mole of hydrogen, we've got 1.008 grams. And that comes out to be 5.449 moles of hydrogen. Okay. All right. How about oxygen? What's the molar mass of oxygen? What is it? 15.999. So that comes out to be 1.816 moles of oxygen. All right, so I know how many moles are there. What's the next thing I need to do? Well, I'm at one of the several points where my goal is to get to integers, right? Absolutely. Okay, so step 2, okay, is going to be divide all by 1.816 because that's the smallest number here, and 1.816. Actually, I'm going to erase the moles there. 1.816. So this is going to give us, hopefully, our empirical formula. If not, we might have to, if we have a non-integer number, we're going to have to multiply by something to get to an integer number. But it's a kinder, gentler Monday, and we wind up with all integers. Okay? So what is our empirical formula? It's going to be C something, H something, O something. What are the things? C, C3, H, 3, and O1. We know we leave off the 1. Okay, so we have our empirical formula. All right, so the next thing that we want to do, okay, is we want to figure out what's the molar mass of our empirical formula. Oops. Because that's need to know information. Okay? So we're going to have 3 times the mass of carbon, 12.011 1.011 gram, and I'm leaving out the grams per mole here. We'll put it on at the end. And then we've got 3 hydrogens, 3 times 1.008. And then we have 1 oxygen, so we're going to add 15.999 to that. And so that comes out to be 55.056 grams per mole. So that's the molar mass of the empirical formula. Is our empirical formula the same as our molecular formula here? Yes or no? Well, the molar mass of the compound, it says, is 110 grams, okay? So that's not the same as 55.05, okay? So they're not the same, okay? So I'm just going to make a note here. Compound's molecular formula does not equal the empirical. Okay. All right, so to get our molecular formula, we're going to divide the measured mass, measured molar mass. It's not the same thing as measuring a mass, right? To determine a molar mass, you got to do a more sophisticated experiment than putting something on a balance. So our measured molar mass is 110.11 grams per mole. And empirical formula mass is going to go on the bottom. And that's 55.056 grams per mole. And so that comes out to be the number 2. So how are we going to get to our beautiful molecular formula? We're going to take our empirical formula and multiply it by that number right there, right? So 3 times 2, H, 3 times 2, O, 1 times 2. Right? And that gives us a formula of C6H6O2. And that's our molecular formula right there. All right. We all feeling good and confident about that? You're feeling good and confident that you need to practice it about 80 times before it kind of becomes second nature. Yeah. All right, so we're going to make this more fun by reminding you of the alum lab, okay? So in the alum lab, okay, you produced a compound that was hydrated. So, hydrated compounds, okay, are those compounds where there's a chemical, okay, and when it's in its crystalline state, when it's in its solid state, okay, there are water molecules that get associated with the molecules in a fixed ratio. Okay, so water molecules associate with that compound in a solid in a fixed ratio. And what that means is there's always the same number of water molecules that are hanging out with my chemical. So if we look at this, okay, let's look at Epsom salts. If anybody has sore muscles and decide to take an Epsom salt bath. So Epsom salt is magnesium sulfate, but in the solid form, it exists as what we call a heptahydrate. Hepta is the prefix for 7, okay? And so what that means is that in Epsom salts, okay, you've got magnesium sulfate molecules, and in the solid form, each one of those molecules has 7 waters kind of attached to it. Okay? They're not covalently bound. Okay? They just kind of hang out due to the general attractive forces between molecules. So when we have hydrates, okay, we use prefixes before the word hydrate at the end of the compound name. To indicate number of waters. So if you've got 10, like in sodium carbonate, we use deca. If you've got 5, it's penta. If you've got 2, it's di. Now, if you have a half of a water molecule, this is, again, it's rare where you will see non-integers, okay? And so this implies that, like, for every 2 molecules, there's 1 molecule of water kind of stuck between them, and we call that a hemihydrate. And again, 5 is penta. So sometimes you have 12, and it's dodecahydrate. Sometimes you have 6, and it's hexahydrate. And so all the standard prefixes that we use for numbers, okay? All right, so the question is, how would you determine the number of waters of hydration that you have? Okay? Well, for most of these solids that are hydrates, you'll notice that they are ionic compounds. Okay? And ionic compounds, because you've got positive charge and a negative charge, and they associate with one another very, very tightly, when you've got that, okay, those things, it's going to take a lot to break them apart, a lot of energy. So you would have to heat them up a lot for the ionic compound to, say, melt and eventually evaporate, to change state. But water, okay, even though water is, associates with itself pretty tightly, it's much easier to evaporate water than it is to evaporate an ionic solid. Okay, so what do? We take our compound, okay, and when we want to figure out how many waters of hydration there are, we heat the water, okay, and we see how much mass gets lost. Okay, so the experiment is you weigh the compound, you heat the compound, you let it cool in a dry place, and then you reweigh it. And the mass that gets lost is how much water was there. And then if you can figure out how many moles of my compound I had there and how many moles of water was lost, then you can figure out that ratio and figure out the number of waters of hydration. Okay. All right, and this is an experiment we actually used to do in lab. We don't do it this semester. I guess we decided not to, just because we had other fun things to do. All right, so your team challenge for today, okay, is going to be trying to figure out, okay, what's the formula and what is the name of a hydrated compound. So you're told that you have nickel 2 chloride, okay, and it's got some waters associated with it. Okay, so the nickel 2 chloride, that is not going to change. We just want to figure out how much, what X is, okay? All right, so you're told what the mass is after you get rid of the water, and you're told what the mass is before the water. Okay, so let's see if you can figure that out. I'll give you like 5 minutes to give it a try. So find a neighbor, and then we'll go through it. Yes. So I'm going to put some hints or in the form of questions up here. Okay, so how many moles of NiCl2 are there after heating? How many moles of water is lost? Okay. You can divide up, and each group person can do part of the problem. All right, so at this point, you should have figured out at least the molar masses of the things you're dealing with. Okay. All right, so who can tell me how many moles of the nickel chloride there were after heating? So you had 0.256 grams, right? And the molar mass is 129.5934 grams per mole. So what did that come out to be? Anybody get that number? It's 0.002 moles. Okay? All right. Did anybody figure out how much water was lost? So you have to figure out what the mass is first, right? How many moles of water was lost? Exactly. So we lost 0.47 minus 0.256 grams, right? So that winds up, and then we were gonna, so that's how much mass, there was. And then we have to figure out how many moles that is, so 18.015 grams per mole. And that comes out to be 0.012 moles, okay? So the question is, what the hell do we do with that information now, right? What we want to know, okay, the big question is, how many moles of water per moles of nickel chloride? Okay, so our desired information is moles of water per moles of NiCl2, right? Because that's what that X tells us. If I have 1 mole of NiCl2, how many moles of water do I have? How many molecules of water, right? So we would take the numbers that we figured out. So we've got 0.012 moles of water, and we would divide it by the number of moles of nickel chloride that I have. And that comes out to be 6, all right? So 6 moles of water per every 1 mole of nickel chloride. So the formula for our compound, okay, our X winds up being 6. So the formula for the hydrate is NiCl2, and then the dot, again, indicates that this is a hydrated compound and that there's no covalent bonds or ionic bonds there. It's just molecules associated with that. All right, so the name of this compound is going to be nickel 2 chloride hexahydrate, okay? So the name is nickel 2 chloride. You just name the ionic compound as you normally would, and then use the prefix hexa to say that there are 6 waters there, and hydrate to indicate that it's a hydrated compound. Okay? All right, so on Wednesday, we're going to be talking about chemical reactions. Okay? We're going to be balancing equations. I'm going to post a like 5 to 10 minute video on balancing equations. Watch that so that what we can do is we can just start with practicing, okay? And you can either bring your group sheets up to me or you can put them in the back and I'll pick them up on my way out.